All right, so today we need to talk about solution concentration. What is that? So I'm addicted to coffee and I like instant coffee. I know that's kind of weird. So the concentration of my coffee depends on how many spoonfuls of that instant coffee I put in there. So if I put 3-4 spoonfuls in there, then I'm dealing with a very concentrated coffee. However, maybe if it's later on in the day, I just put 1 spoonful of the instant coffee, then it's going to be less concentrated. In chemistry, however, we can't just talk about, oh, we put 2 teaspoons of blah, blah, blah compound into the water. That's not going to work. We need to be more precise. So we're going to use a measurement called molarity, and it's very specific. So molarity is the amount of solute. So let's break that down first. The solute is the compound that is being dissolved. Very important here, the solute, when in question, it's always the minority component. The solute is the thing that's doing the dissolving. That's always going to be your majority component. For purposes of our class and a lot of even our day-to-day examples, like we could talk about the concentration of coffee, of Kool-Aid, of juice, it's going to be water. But it doesn't always have to be water. Even in the lab, we sometimes use ethanol or dichloromethane, or we have a bunch of them that we could use, but in the Gen Chem labs, we typically have water being our solvent. Alrighty, let's talk about some examples of solutes. So you definitely have solid solutes available. And I put AQ up here because concentration and solubility go hand in hand. If I have something that's soluble and I'm going to put AQ, then on that bottle, I need to write a number that tells the person how concentrated is this solution. How much of that soluble stuff did I put in there? So, for example, we know sodium chloride or table salt is very soluble. So that might be one of our solutes. Especially like if you go to the ocean, we can say, well, salt, sodium chloride is a solute that we find in ocean water. Other examples, anything that's soluble. So we could also do potassium nitrate. So any kind of solid salts that will dissolve are considered solutes. You don't have to limit the argument to just solids. You can also have liquid solutes. So you could take, I'll use ethanol as the example here, CH3, CH2OH. So this is the alcohol that we drink, so basically vodka. But ethanol is soluble in water. So if a chemist, and they do this for different reasons in the lab, if a chemist takes 10 milliliters of ethanol and adds 90 milliliters of water, well, now we have a solution. We have 2 things that are mixed up, and the ethanol would be the solute because there's less of that in it. Last thing here, which always blew my mind, our solute doesn't have to be a salt or a liquid. It could be a gas. So think about soda. Soda has carbon dioxide in it. So we could say the carbon dioxide is a solute in the soda, which is mostly water at the end of the day. Soda is also interesting because it has multiple solutes. You don't just have to have one solute. You can have carbon dioxide, the sugar, the flavoring. As long as they're all minority components, we could call them solutes. When you buy jewelry, you typically don't, like if you have gold jewelry, it's not 100% gold. There's going to be something else in there to strengthen that gold a little bit. So even metals can have, metal alloys can have solutes. So with jewelry, right, it's maybe they put some zinc in there, mixed in with the gold to give the gold strength. So our solute would be zinc, but our solvent, it's kind of unusual, but our solvent would be our solid gold. And let me put in alloys. So in an alloy is a metal, a combination of two or three or four elemental metals, and so they combine them to give them strength and help them not corrode as quickly because of oxidation. So many examples. I could go on and on. This makes such a fabulous class discussion because people think of so many examples from their day-to-day life. So definitely, if you have any questions, you're like, I thought of this. What's the solute? What's the solvent? It's always fun to kind of break those things down. Solution, another important term. So you need to know all these terms. You need to feel comfortable with them. Solution is everything. So it consists of all your solutes, like in the case of soda, there's multiple solutes, and then the solvent, the thing that's the majority component, the thing that's dissolving everything else. So back to the calculation. So you have molarity. That in the numerator, you're going to have the amount of solute. It's very important that this is in moles. And then in the denominator, we have liters of solution. It has to be liters. You can't use milliliters or anything like that. So when I memorize it, and this is a formula that chemists, biologists, we use day in and day out. Molarity is moles over liters. That's what's going to stick with you. But these are the units, but it's also the formula. Moles of solute over liters of solution. You could write moles over liters. That's perfectly acceptable. More common, you'll see a capital M, and it has to be capital. The little m's are played out, right? We already have little m for milli and meter and mass. So make sure you're throwing a capital M on there, and that capital M will take the place of moles over liters. So we'll jump into some calculations. In our first problem here, we're given moles and we're given volume in liters. So I'm going to use the formula, molarity equals moles over liters. And remember, this formula is very specific in terms of units, but we're already all set here. So we'll put the moles in the numerator. So 0.38 moles divided by 6.14 liters. So we get an answer of 6.1889. It goes on and on and on. 9 blah 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 times 10 to the negative 2 molar. I only have 2 sig figs because this only has 2 sig figs right here. So I'm going to write this as 6.2 times 10 to the negative 2 molar. And if you're labeling something, or even in these problems, we would want to be specific. So I'll call it 6.2 times 10 to the negative 2 molar lithium nitrate. And then the best way would be to put AQ, if you know, typically this is aqueous, if you know that they used water as the solvent. This is in scientific notation. It's fine like this. You could also report this as 0.062 molar lithium nitrate. Either way. Alrighty, so on this next one, we have a little bit more going on. We're starting with grams, but remember, we need to use moles. And then they also gave us milliliters, but we need to use liters. So we need to do some conversions before we use the molarity equation. So I know I can go from grams to moles using molar mass. So let me calculate my molar mass. So 2 carbons, so I'll do 12.01 times 2. 6 hydrogens, I just combine them all. So 1.01 times 6, and 1 oxygen. So that's 16 grams. And all of these have units of grams. So when I did that earlier, I got a molar mass of 46.08 grams per mole. Now that we have the molar mass of the ethanol, we can convert it to moles. So I'm going to do 290 grams. I want grams to cancel, so that'll go in the denominator. So I'll say there's 46.08 grams in 1 mole. Grab my calculator and divide that real quick. I get 6.2934. Don't round it. There is a couple more digits. At the end of the day, right, I'm just going to have 2 sig figs. Don't round it at this point. Keep extra digits until you're done with the calculation. Ideally, you'd have the whole number, all the digits. So here I have 545 milliliters, and I need that in liters. So this is cool. This is the earliest material in the course, right? We know there's 1,000 milliliters in 1 liter. So this is going to be 0.545 liters. Now we're ready to use that molarity equation. So molarity equals moles over liters. So I'm going to put the 6.2934 up top. And then 0.545 liters in the denominator. Divide that out, and I get 11.5475, quite a long number, but we only have 2 sig figs because this didn't have a period on it. So I'll write the whole number first. Blah, blah, blah. But I'm going to change it to 2 sig figs. So at the end of the day, I'm going to say I have 12 molar, and they didn't, ethanol. And this is what I would put on the bottle if I had prepared this solution and I was going to make a label for it. So some more practice calculating molarity. These examples are very similar to the previous one in that we're given grams and volume in milliliters. And you might wonder, why are these units so emphasized? These are the units that we work with in the lab, right? You'd measure something out on the scale in grams, and you'd use a graduated cylinder or some other piece of glassware. Those typically have milliliter markings. So again, this is the most common way. Let's do the molar mass of our sucrose. So we have 12 carbons, 12.01 grams times 12, 22 hydrogens. So I'll do 1.01 times 22 and 11 oxygens. So 16 times 11. And if you have slightly different values there, don't worry. I mean, we'll probably get the same number in the end, even if you're using a different periodic table. So I got 342.34 grams as my molar mass. So I'm going to take the 15.4 grams and write that 1 mole has 342.34 grams. And that gives me, when I divide 15.4 by 342.34, I get 4.498 0.45 times 10 to the negative 2 moles. At this point, now that I have moles, I need to convert this to liters. So again, since this is so common, you don't always have to show the setup for this. But I'm going to do it again just for to see another example. You're going to divide by 1,000 because 1 liter has 1,000 milliliters. What you're going to wind up doing in every single case when you're going from milliliters to liters is you're going to wind up moving the decimal point 3 places to the left. So 1, 2, 3. So we get 0.074 liters. So if you want to use that shortcut, by all means, especially if you already feel confident setting it up. We're not done yet. We still need to throw both the moles and the volume into our molarity formula. So we'll do molarity equals moles over liters, and I have the 4.49845 times 10 to the negative 2 moles. I cut that number off a little bit. I was running out of space, but I still have the complete number displayed in my calculator, because remember, we're not supposed to round until we get to the very end of the problem. And then I'm going to divide that by 0.074 liters. I get 0.607 898. It goes on and on. Let me check my sig figs. There's 3 sig figs here. I shouldn't have dropped that last 0. It is significant, right? Because the number they initially gave me was 74.0 mils. So that has 3 sig figs. And then my mass also had 3 sig figs. So I can report my molarity to 3 sig figs. So I'm going to report it as 0.608 molar. And we always want to put the identity of the substance. So I'll put the formula for the sucrose, C12H22O11. And I keep on assuming, just because it is what typically happens in the organic lab, is that these are aqueous solutions. We always want to make note of the solvent as well. One thing to note before I move on to the next problem. On the examples, when I was describing what is a solute, I threw a bunch of ionic compounds at you. But there are covalent compounds that are soluble. The difference is ionic compounds split into ions when you dissolve them. The sucrose, because it's covalent, stays as one whole thing when we mix it with water. It's not going to break. It's going to dissolve, but it's not going to break apart or dissociate because it's covalent. All right, moving on to the next one. Let's see. Sodium is 23 grams. Chloride is 35.45 grams. Try to do that in my head, but I'd embarrass myself. 58.45 grams per mole. So I'm going to start with the 9 grams. 1 mole has 58.45 grams. And I get 0.1539, and then there's a whole bunch of 7s, and the number just continues and continues. So this will be the moles of sodium chloride that I'm trying to dissolve. I'm going to use the shortcut here. I'm going to divide this by 1,000, but in my head what I do is I just move it 1, 2, 3. So I'm going to have molarity equals moles over liters. So 0.153977 moles. Whole numbers in my calculator. I didn't round it in my calculator. I'm going to divide by 0.0864 liters. And here I get a molarity of 1.782149. Keeps on going. Let's look back at sig figs. 3 sig figs with the 9 grams and 3 sig figs with my volume. So I'm going to report this as 1.78 molar sodium chloride. Last thing I want to mention, you've seen a range of concentrations. We have 0.608, there was an 11.5 or something like that in the previous problem, 1.78. Concentrations can be super small. We can keep on diluting something and adding more and more water. There is an upper limit on concentrations. I don't ever see concentrations above 20. So why that is because eventually things that are soluble, think about salt, like salt that you'd see in the ocean, sodium chloride, right? Eventually, if you keep on pouring salt into a glass of water, you can stir all day, but it's not gonna continue to dissolve. So there's gonna be a maximum, and it depends on the compound, there's gonna be a maximum amount that dissolves in that solvent. And it doesn't go beyond 20. So if you do this calculation, you get 100 molarity, double check your work. You did something wrong because your numbers should not be larger than 20. However, they can be super small. In the previous examples, we were solving for molarity. Now we're going to work these problems from a different direction. Here, they're asking us to solve for the moles of magnesium chloride. If I'm solving for molarity, I usually do molarity equals moles over liters. However, if I'm solving for anything else, moles, grams, volume, then I do take advantage, or I like to take advantage of conversion factors. So if I have 2.00 molar magnesium chloride, that means two things. So let me put my little thought bubbles. That means I have 2.00 moles of magnesium chloride in 1 liter. Or like always, right? We can flip that. So I can also say 1 liter has 2.00 moles of magnesium chloride. So a molarity, if you're given a molarity, think about it as a conversion factor. Alrighty, so let's set up the problem here. Just like separate my thoughts from the rest of the problem. So I'm going to start with 60 mils. And I know I want to get to moles. I see that I have a relationship between liters and moles. So let's get this to liters first. So I'm going to say there's 1,000 mils in 1 liter. And milliliters cancel milliliters. And then I come back over here and I'm thinking, if I use this first setup of the conversion factor, then liters will cancel liters, and then I'm just left with moles. So 2.00 moles of magnesium chloride per 1 liter. And then again, liters will cancel liters. So now in my calculator, I have to do 60 times 2, put it in parentheses or hit enter at that point, divided by 1,000. And I get 0.120 moles of magnesium chloride. My units are right here. All right, let's see that technique in a couple more situations. Here we're asked to solve for the mass of potassium iodide. I did the molar mass ahead of time because I knew I would need that. Start with what they gave us. So they're saying that we need to prepare 500 milliliters. And so I'll start with that. I don't want to start with the molarity because this is going to be my conversion factor. So I always leave that one until like I actually need it. And so in my head, again, I'm thinking this is 2.80 moles of potassium iodide per 1 liter, or I can flip that. So right now I'm in milliliters. We need to get rid of the milliliters. And milliliters is gone. Now I need to get rid of the liters. And I want to go to moles. I can use that conversion factor. So I'm going to say there's 2.80 moles of potassium iodide in 1 liter of this solution. I'm not there yet though, because the problem asks to solve for mass in grams. But now that I'm in moles, I can tack on my last conversion factor. I know that 1 mole of potassium iodide, I'll grab my molar mass, has 166.002 grams of potassium iodide. So moles cancel moles, and I'm just left with grams. And I'll plug all that into my calculator. So 500 times 2.80 times 166.002 divided by 1,000. And it looks like if we were trying to prepare a 2.80 molar solution, potassium iodide solution, we would need 232 grams of potassium iodide. Once again, we're asked to solve for grams of our solutes. In this case, grams of potassium dichromate. I went ahead and calculated the molar mass of potassium dichromate ahead of time. I knew I would need that since we're asked to solve for grams. Remember, the molarity is our conversion factor, so I'm going to hold off on using that until I actually need it. I'm going to start my problem with this volume. So I have 250 milliliters, and I want to turn that to liters. And then I'm going to use my molarity. There's 2.16 moles of potassium dichromate in 1 liter of that solution. So mils cancel mils, liters of liters. Now I'm at the mole unit. So I'm going to say 1 mole of potassium dichromate has 294.188 grams of potassium dichromate. And so moles will cancel moles, and I'm just left with grams of potassium dichromate as my unit. So in my calculator, I'm going to do 250 times 2.16 times 294.188, and I'm going to divide all of that by 1,000. That gives me 158.86 grams. I do have to consider sig figs here. So I'm going to go with 2 sig figs because there's no indication that this last 0 is significant. So I'm going to say I need, my final answer would be I need 160 grams of the potassium dichromate. Alrighty, so in these problems, we're asked to solve for volume. This is a very realistic situation. You know how many moles you need, and you have a specific concentration available. Then the question becomes, well, how much do I need to pour out of that container? Again, same kind of approach where I'm going to leave my molarity until I need it because that's going to serve as my conversion factor. I'm going to start with the moles. So the student needs 1.75 moles. It doesn't tell us of what, so I'll just leave it at moles. And then we know that there's 1.25 moles per 1 liter. However, looking at that version of it, that's not going to help me. So I need to use the flipped version. I'm going to say 1 liter has 1.25 moles. And that's the entire problem, right? Because they asked us how many liters should the student use. So I'm going to do 1.75 divided by 1.25. And I get 1.40 liters. Once again, we're asked to calculate the volume, and we have 1.09 molar, which is going to serve as my conversion factor. So I'm going to start with the fact that we have 8.29 millimole. We can't work with millimole. It has to be in moles if we're using the molarity. So I'll get rid of the millimoles first. There's 1,000 millimoles in 1 mole. And now I can say that there's 1.09 moles in 1 liter. So moles will cancel moles, millimoles will cancel millimoles, and I'm left with liters. They weren't very specific about the volume, so I'm just going to leave it in liters. So I'm going to do 8.29 divided by 1,000 times 1.09. I get 7.61 times 10 to the -3 liters. And actually, that number is kind of ridiculous. I'm going to multiply it by 1,000, and we have 7.61 milliliters.